Okay, well, good morning, everybody. The first lesson, AP Computer Science A, we're going to start at the origin. We're going to start at the very beginning. We're going to start with what computers are all about, and that is basically a series of highs and lows, off and on, electrical impulses that get interpreted as zeros and ones, and those zeros and ones, they get interpreted as sound files, JPEG files, and a whole host of things that you're familiar with when you work with your mobile device, a PC or whatever. So we're going to start with base 10, something you know. In base 10, we have 10 digits, and the 10 digits we work with are 0 through 9. Okay, we're working with powers of 10, base 10. So when we have a number like 9,047, using base 10, I can represent 9,047 this way. So, well, first, I have 10 to the 0, 10 to the 1, 10 to the second, and 10 to the third. 10 to the third is 1,000, 10 to the second is 100, 10 to the first is 10, and 10 to the 0 is 1. So using the digits 0 through 9, I can take those digits and multiply it by powers of 10. So I have 9 times 1,000, which is 9,000. I have 0 times 100, which is 0. I have 4 times 10, which is 40. And I have 7 times 1, which is 7. So I'm taking the digits 0 through 9 and the digits 0 through 9, and I'm multiplying them by powers of 10. Okay, to give me 9,047. And that's how I know that in base 10, 9047 is 9,047. All right, but now we'll look at base 2, or binary. Okay, base 2, we only have 2 digits to work with, 0 and 1. 0 and 1. So how do we represent numbers in base 2, or binary? Well, let's take a look at this. So let's say here I have this number in binary 1101. I am not going to say 1,101 because that would be incorrect. I'm working in base 2. But in base 10, that would be equivalent to 13. Base 10. So how do I get from 1101 base 2 to 13 base 10? Well, very easy. Because I'm working with base 2, I'm working with powers of 2. Okay, so 2 to the 0, or 2 to the 0 is 1, and then 2 to the 1 is 2, and 2 squared is 4, and 2 to the third is 8. Okay, so now, just like with base 10, where I took the digit and I multiplied it by the power, I'll do the same thing in base 2. I'll take the digit 1 and multiply it by power of 2, which is 8. So 1 times 8 is 8. So again, I'm taking that digit there, 1, and I'm multiplying it by 2 to the third. Okay, because I'm working with base 2, and I got 8. And then I'll take the other one, and I'll multiply that by 2 to the second. So 1 times 4 is 4. Then I take that 0, and I'll multiply it by 2 to the first. Well, that will give me 0. And then finally, I'll take that 1, and I'll multiply it by 2 raised to 0, which is 1, and 1 times 1 is 1. So 1101 base 2 is 13 base 10. 8 plus 4 plus 1 is equal to 13. No different than if we're working with the procedure is the same, except we have fewer numbers, and we have a different base. But the algorithm is the same. Same old stuff. All right, so let's take a look at some of these things. Now, in base 2, 8 bits makes a byte. In DE, we would say this here. So 4 bits equal a nibble. And then 2 nibbles equal 1 byte. Or 8 bits equal 1 byte. All right. So let's take a look at that an example 2. Okay. So again, I've represented powers of 2. I'm working with 8 bits, so or a byte. So I'm going to work with powers of 2 all the way to 2 to the 7th, 2 to the 6th, 2 to the 5th, 2 to the 4th, so on and so forth. Now, so I'll work with the number here then, 0, 1, 0, 1, 0, 1, 1, 0, base 2. We'll see that's 86 base 10. So again, how do we do that? All right. So again, we take the 0 and we multiply it by 2 raised to the 7th, or 0 times 128. That's 0. We take the 1 and we multiply it by 2 raised to the 6th, or that's 64. We take that 0 there, we multiply it by 2 to the 5th, and that's 0. We take the 1, that 1 there, we multiply it by 2 to the 4th, and that's 16. We take the 0, we multiply it by 2 to the 3rd, that's 8. We take the 1, we multiply it by 2 squared, that's 4, and we continue on. And you see if you add up the numbers 64, 16, 4, 2, we get 86. Okay, it's kind of easy to see, if I go back up to this example, whether or not a number is even or odd. From base 2, it's easy to see if a number is going to be even or odd. Pause the video and see if you can figure out how. Okay, well, you probably came to the conclusion that if the byte, let me say this too. So with a byte, we say this is the least significant bit, LSB, because it adds the least. And over here, this is the most significant bit because it adds the most, right? So if the least significant byte is on, or 1, then we know it's going to be odd. If the least significant byte is off, or 0, we know that the number will be even. All right, here's an important thing. The largest number you can represent with n bits is 2 raised to the n minus 1. So here I have a byte. What's the largest number you can represent with a byte? Well, if all the bits are on, I have 1, 1, 1, 1, 1, 1. Okay, but what is that? That is 255 base 10. Take 2, raise it to the 8th, you get 256 minus 1. That's 255. All the bits are on, so we're multiplying each bit by the respective powers of 2. And you get 255. Okay. So pause the video and see what would this number be. And 1, 2, 3, 4, 5, 6, 7, 8. Try that. Pause the video, see what that number would be. And maybe one other one. 0, 1, 0, 1, 0, 1, 1, 2, 3, 4, 5, 6, 7. Well, what would that number be? Base 10. So these are base 2 right here. Well, what is that number base 10? All right. Now from decimal to binary, think largest powers of 2. All right. And again, I have included powers of 2 because that helps me as I'm going the other way. So here I have the decimal number 137, that's base 10. Well, what is that base 2? Well, here, so I asked myself, well, the largest power of 2 and 137 is 128. So bit 8 is on. So this is the first bit here. This is the first bit, second bit, third bit, fourth bit, fifth bit, sixth bit, seventh bit, 8th bit. The 8th bit is on. All right. The 8th bit is on, so I'm going to put 1 there for the 8th bit. Now 137 minus 128 leaves me with 9. So now I say, what's the largest power of 2 and 9? Well, that's 8. Okay, so that means bit 4 is on. That bit there, it's on. And so 9 minus 8 is 1. Largest power of 2 and 1 is 1, so bit 1 is on. Okay, so that bit is on. All right, so there. So 137 base 10 is 10001001 base 2. Okay, here's another example. 24 base 10. What is that? Base 2. So the largest power of 2 and 24 is 16. So bit 5 is on. Okay, bit 5 is on. That bit there. 24 minus 16 is 8. The largest power of 2 and 8 is 8. So bit 4 is on. All right. Or bit 3 is on, I'm sorry. No, 4. Largest power, so that should be, that's ours is 8, so bit 4 is on. There we go. All right, so then we get a difference of 0, which means no other bits are on. All powers of 2 have been exhausted. So 24 base 10 is 0011000. All right, so try these numbers here. What would 243 base 10 equal base 2? And then maybe 164 base 10. So try that. What would 243 base 10 equal? And what would 164 base 10 equal in binary? Okay, now we get into base 16. So with base 10, we had 10 digits, 0 through 9. That was base 10. Base 2, we have 2 digits, 0 through 1. So again, we had 10 digits here. We had 2. So base 16, or hexadecimal, we should have 16 digits. Well, I'm going to have a little bit of a problem. Okay, oh, that was base 2. Base 16, well, we'll have the digits 0 through 9, but that's only 10. We need 6 more. So the largest number we can have, base 16, is 15, just like the largest number we had. Base 2 was 1, and the largest number we had, base 9, was 10. Okay, the largest number we have to have for base 16 is 15, but we're going to use A to represent 10, B 11, C 12, 13 is D, 14 is E, and 15 is F. Okay, but again, we're working with powers of 16, not powers of 2 or powers of 10. All right, so here, let's take a look at this example here. C3B2, base 16, well, what is that? Well, C is 12, so we're going to take 12 and multiply it by 16 raised to the third, which is 4096. And then we take the 3, and we're going to multiply it by 16 raised to the second, which gives me 768. And then we take B, which is 11, and we'll multiply it by 16 raised to the first, which is 16. And then we take 2, and we multiply it by 16 raised to 0, which is 1. Okay, so we get 49152 plus 768 plus 176 plus 2. Yeah, and that's 50098. Okay, so C3B2 base 16 is 50098 base 10. Again, the procedure, the algorithm is the same. You take the digit and you multiply it by the power of the base. Okay, everything's the same. The process is the same. So what if we go back the other way? From decimal to hexadecimal. Think largest power of 16. Example. So let's say here I have 11,420 base 10. What is that base 16? Well, the largest power of 16 in 11,420 is 496. But it occurs at a multiple of 2 times. Okay? 4096 times 2 is 8192. So we take 11,420 and we subtract 8192. 4096 times 2, we get 3,028. All right. So keep that number, keep that in mind, that too. Now, what's the largest power of 16 and 328? Well, it's 256, but it occurs at a multiple of 12 times. Oops. So we take 3228 and we subtract 3072, or 256 times 12, and we get 156. And then we say, what's the largest power of 16 and 156? Well, that's 16, but that occurs at a multiple of 9 times. So 156 minus 16 times 9, that's 12. Then we say the largest power of 16 and 12 is 1. And that occurs at a multiple of 12 times, or 1 times 12 is equal to 12. Okay, so 12 minus 1 times 12 is 0, so all powers of 16 have been exhausted. Okay, so here we have 11,420 is 2, 12 was C, 9, and then 12 was C. So it's 2C, 9C. 2C, 9C, base 16. Again, we're just subtracting off multiples of power of 16. All right. All right, but the process is the same. Let me take a look here. Yeah, that's maybe just a little base from decimal to base 16. It's just a little more work. Okay, yeah, it's just a little more work. All right, a little more thought involved there. Because you got to consider the multiples, right? You have to think multiples. It makes it a little more difficult. All right, but the process is kind of the same. All right, so here, so each 4 bits represent 1 hexadecimal number. So 111 base 2 is 15 base 10. Okay. So how do I know 111 base 2 is 15? Well, okay, so I have 8, 4, 2, and 1. 8 plus 4 plus 2 plus 1. Okay, that's 15. And that's F, base 16. And then 1010 base 2, how do I know that's 10? So that's just 8 plus 2. That equals 10. Well, that's A, base 16. And then 010, so that's 4 plus 1. So that's 4 plus 1, that's 5. It's 5 base 10. Well, that's just 5 base 16. Each 4 bits represents 1 hexadecimal number. So it's kind of easy then to go from binary. So from binary to hex, because you just work with sets of 4 bits. Work with sets of 4 bits there. Okay, so if I split up into 4 bits a nibble, 1, 1, 0, well, that's 8 plus 4 plus 2. 8 plus 4 plus 2, that's 14. 8 plus 4 plus 2, that's 14, base 10. And then 0, 1, 1, that's 2 plus 1, and that's 3. Well, 3 is 3 in base 16, but 14 is E. Let me see if I go back up here. Where is... Yeah, 14 is E. All right, so 1, 1, 1, 0, 0, 0, 1, 1, base 2 is E3, base 16. All right, and what would that be? Base 10. Well, that would be E is 15, so that would be 15 times 16 raised to the first plus 3 times 16 raised to the 0. Right, whatever that is. We should get the same thing here. Just let me do some calculations. I always like to check my work here. Make sure it is what I'm talking about is right. And then so 15 times 16 plus 3, and that would be 243. Well, let's verify that. If we just worked in binary. Okay, so here, binary. Let me go up here. I'm working with powers of 2. Even I forget this sometimes. So we'll start with 128. All right, so here I have 128. I'm working with these there. Plus 64, plus 32, and then plus 2 plus 1. All right, so if I don't get 243, I'm a monkey's uncle. 128 plus 64 plus 32 plus 3, and voila. What did I get? 128, 64, 32 plus 3, I get 227. E is, oops. I bet you I did something. Oh, E is 14, not 15. There, check my work there. I want you guys to know I did that intentionally. You always learn from mistakes. All right, so here, let's do that again. So that is 14 times 16 plus 3, and that's 227. Yeah, there we go. Now that works. Okay, happy face now. All right, so it works. I'm kind of a big eye, but I got a happy face. It all checks out. All right, so there. So that's an overview of decimal, binary, and hexadecimal. It's much more of an overview than the textbook will give you. That's for sure. All right, so review the video if you get stuck with anything. Now we go on to logic gates. Okay, and gates, or gates, and not gates. All right, and I present this a little differently than the way the book presents it. They, for their truth tables, they use I think high and low, or true and false. They use true and false. I just do a binary count. Okay, I do a binary count. So they use true and false. Okay, and computer science, true is 1 and 0 is false. I mean, we also in DE, or in terms of electricity, if something is off or on, you can think high and low. Okay, high and low. It all means the same. I use truth tables. I use a binary count in my truth tables. The textbook will use true and false. I don't like that. I've taught DE, and we work with binary count in truth tables. And when I say binary count, we have 2 bits here. So 0, 0. If you think in terms of 2 bits, that's 0. And then 0, 1, that's 1. And then 1, 0, that would be 2. And then 1, 1 would be 3. So that's why I say it's a binary count, 0, 1, 2, 3. All right, the textbook presents it much differently. But anyway, with logic gates, we have with the AND gate, we have two inputs, A and B. Okay, and the output, if both bits are off, A is 0 and B is 0. Think in terms of electricity. If there's nothing on, then there's nothing on. Okay, so for an AND gate, okay, a 0, 0 gives you 0. If one of the inputs is on 0, 1 or 1, 0, you still get a 0. Okay, in order to get a high or a 1, both bits have to be on. And okay, both of them are on. 1, 1 gives you 1. So that's an AND gate. An OR gate, either one or both of the bits have to be on for you to get a high. So 0, 0 gives you 0. 0, 1 gives you 1. 1, 0 gives you 1. 1, 1 gives you 1. If either of the bits is on, if either of the inputs is high, you get a high. All right. We're going to learn. We're going to learn when we actually get into programming. There's such a thing called short circuit. So when we have a Boolean expression that uses an AND, if one of the inputs is false, then we just short circuit out of it. Okay, the computer doesn't do any more checks. It just knows that, okay, the output is just false. If one of the inputs is false. But if we're working with OR statements, compound OR statements, okay, we just can't short circuit. One bit could be off, but we have to check to see if the other condition is true. Okay, we can't short circuit. Okay, but with AND we can. All right, here, so, and then we have the NOT gate. Basically, it's just, you just negate the input. So if the input is 0, the output is 1. If the input is 1, the output is 0. So know the gates, know what they mean. Yeah, AND gate, OR gate, NOT gate. NOT gate, there's only one input. And again, I use truth tables. I use truth tables or binary count tables for my truth tables. The book does it a little differently. And then they present an exclusive OR, which just means that for you to get a 1, only one bit, only one, has to be on. The other one has to be off. Any other condition, and you'll get a false. All right, so I'll just walk you through this here. So let's say here if the input A is 0, okay, I know that because this is AND, I'll get a 0. I don't even have to check this input. I don't need to check that if that input is 0. All right, let's look at something else. Okay, so let's say that's 0. Well, that's going to be 0. Oh, wait a minute. Okay, I didn't finish it up. So if A is 0, then that AND will be 0. I know that. But if B is 0, so this is 0. Well, that's an AND statement. That's going to be 0. Okay, so I got 2 zeros going into an OR. That's going to be 0. Now what happens if B is high? So this would be high. So this is 1. And again, this AND doesn't matter. It's going to be 0 because A is 0. So that's 1. But now the 0 becomes 1 because that gets negated. So I have 2 1s going in. I have 2 1s going into the AND. So that's going to be 1. And so I'll get a 1. All right. Now if I look at what happens if A is, so this would be 1. A is on. B is 0. B is 0. But that goes there. That gets negated. So that's 1. And I don't need to do anything more because this is OR. Because I have a 1 going into an OR, then that has to be 1. Okay. I don't need to check all of this here. Oh, I said something about short circuit. Maybe I was mistaken. Okay, you short circuit. Well, you short circuit in two cases. Well, anyway, let's just skip that for now. But anyway, so that's the exclusive OR. And then what happens if both of them are on? Okay, so let's take a look at here. So if this is 1, if that's 1, okay, so that's 1, this becomes 0, and that becomes 0 because that's an AND. All right, so this is 1, A is 1, this becomes 0, and that's 1, and so that becomes 0, and so you get 0. All right, so that's an exclusive OR. Okay, only one of the inputs must be on, only one, for you to get a 1. Do we use exclusive OR a lot in programming? Well, maybe not so much at the software level, but they're very important at the hardware level, and they help a computer count. In DE, we learned that exclusive OR gates are very important in terms of counting. We call them binary adders. It's essential way a computer does multiplication or addition. Okay, exclusive OR. Okay, and then the last thing I wanted to talk about is the ASCII table. Okay, so how does the computer interpret those zeros and ones your keyboard presses into text or whatever? Okay, so we have this ASCII table. Okay, so when you press the keyboard, for example, if you press on the keyboard the number 1, okay, the decimal representation of that is 39. The hex representation, it's 8 bits. Or that's base 8. Hex, no, that's base 16. Base 8 octal is 61. And then, okay, but the decimal representation is 49. The hex is 31. And the octal is 061. But in any event, that number 49 can get represented as zeros and ones, and can get represented as a binary number. So when you press the number 1 on the keyboard, basically you're sending a series of pulses, zeros and ones, that the computer will interpret as a 1. Okay. All right, and so that would be the case for any keyboard character you press. They have a decimal, octal, hexadecimal representation. They also have a binary representation. But again, at the very basic level, a computer is nothing more but a series of electrical impulses off and on, zeros and ones, highs and lows. Okay, electrons floating around. And those zeros and ones, those highs and lows, those off and ons, they get interpreted as everything you know about a computer. And it's very basic level. A computer is nothing more but all physics. And that's what DE students would say. And anyway, here guys, so that's it for the first lesson. Okay, so I want you guys, just for your assignment, and this is in chapter 1 of the textbook, I want you to do 1 through 4A. 10 through 16. And then tomorrow, the next day, you guys will read the rest of the chapter, but that will be online, and then you'll answer some more questions. You'll answer some more questions in the textbook. Now, let me just see here. 1 through 4A, I believe that starts on page 5 of the textbook. All right, but I don't think it's going to be necessary to read the online portion of the book, sections 1.2 to 1.7, to be able to do 1 through 4A, in 10 through 16, because I've gone over all of that with you. And then you'll have to read the next day online 1.2 through 1.7 to answer the other questions. But just for today, do that. All right, so guys, that's a wrap. That's the first assignment. And then we'll finish up that chapter tomorrow.